In the discussion about constrained motion, we neglected the friction between moving bodies. The concept of friction comprises all the phenomena related to the relative displacement and the resistance of such a displacement along the surfaces of solid bodies in contact, while they are sliding or trying to slide across each other. We can classify these phenomena in many different ways, but here we will focus on two types of them: sliding or kinetic, and sticking or static friction. Sliding or kinetic friction describes the situation where a solid body slides on the surface of another one, and we talk about sticking or static friction when the surface of a body adheres to the surface of another one rather than slides against it. In such cases, the bodies in contact are at rest and can be set in motion with respect to each other by exerting a given amount of force on any of them, so that the resistance due to friction could be overcome. Let us start with the discussion of sliding friction. If we place a block on a table and push it with a given initial velocity v0 along the surface of the table, then the velocity of the moving block will decrease and the body stops at some point, where its velocity becomes zero. The decrease in its velocity v and the deceleration of the body, or its acceleration a pointing to the opposite direction of the velocity, are attributed to the frictional force exerted on the body by the surface of the table. Based on the second law of motion, this force is measured by the product of the mass of the body and its acceleration. The law can also be used to measure frictional force in a static force measurement, where we exert a given amount force F' on the body in the horizontal direction by connecting a weight to the body with a spring over a pulley attached to the table and suspending the weight. We can measure the force F' with a spring scale inserted between the block and the pulley. For a proper choice of the weight pulling the block will still remain at rest. By pushing the block on the table we can set the body in motion. In the experiment we will find that the block performs a uniform linear motion, that is, it moves at constant velocity or vanishing acceleration. The second law of motion tells us that the net force F acting on the body, given by the product of its mass m and its acceleration a, must vanish, therefore another force is exerted on the body which has the same magnitude as the force F' but points in the opposite direction. This force is the frictional force exerted on the block while it is sliding on the surface of the table. Instead of the weight suspended from the string, we can also use an electric motor with its axis connected to the block via a spring scale such that we could move the block over the surface of the table. If we switch the motor on and operate it at a low rotation speed, then the string will be coiled up on the rotating axis. As a result, the string exerts the force F' on the body and drags it along the surface of the table at constant speed. The frictional force acting on the block can be measured by the spring scale, since this force is just the opposite of the force F' exerted by the string. In this setup, the result of the experiment depends on several parameters and we can modify them to study their effect on the frictional force produced by the moving block. We can change the area of the contact surfaces between the block and the table by placing it with another face on the table that has different area. We can change the velocity of the sliding body by modifying the rotation speed of the electric motor. We can change the magnitude of the force applied on the body in the direction perpendicular to the contact surfaces by placing a weight on the block. Finally, by replacing a block with another one which is made of a different material, we can change the physical properties of the surfaces sliding against each other. Such a comprehensive experiment was performed by Coulomb, who used a spring-driven setup in his experiment. His findings on the quantitative relationship between the frictional force and these parameters are called Coulomb's law of friction. If we consider two bodies sliding against each other at a constant velocity v where the force N applied on the bodies points in the direction of the surface normal of the contact surfaces, then the law states the following about the frictional force exerted by the bodies on each other. The direction of the frictional force is opposite to the velocity v, describing the motion of the contact surfaces with respect to each other. The magnitude of the frictional force is directly proportional to the magnitude of the applied force N in the normal direction of the contact surfaces. The magnitude of the frictional force depends on neither the area of the contact surfaces nor the magnitude of the velocity of their relative motion. In mathematical terms, Coulomb's law of friction states that the frictional force produced by the sliding contact surfaces is equal to minus a proportionality constant mu times the magnitude of the normal force N, times the relative velocity v divided by its magnitude. Minus the normalized velocity provides the direction vector of the frictional force, and the proportionality factor mu is known as the coefficient of the sliding friction. In this table, this coefficient is given for some pairs of different materials. We can see that mu is equal to about 0.5 for wooden bodies sliding against each other, which means that the frictional force is about the half of the normal force acting between their contact surfaces. The coefficient of sliding friction is equal to about 0.1 for bodies made of steel when they are sliding against each other, that is, the frictional force is much smaller than the one produced for wooden surfaces for the same normal force. The friction between an ice lump and a steel surface is even smaller since the coefficient μ for this pair of materials is equal to 0.014. In the experiment studying the friction of the sliding block on the table, the block was dragged along at a constant speed, which means that the net forces acting on the body vanish. If the magnitude of the force F' pulling the body is not equal to the magnitude of the frictional force produced by the contact surfaces, then the body will perform an uniformly accelerated motion. In a special case the pulling force vanishes, that is if we push the block and reduce the force F' to 0, then the instantaneous velocity v of the sliding body is reduced to 0 by the frictional force exerted on it by the table. As a result, the block covers some distance during its deceleration and finally stops. We can apply the second law of motion to determine the magnitude of the acceleration A of the body, which is given by the ratio of the magnitude of the frictional force acting on the body to its mass m. We already determined the magnitude of the frictional force of the horizontal sliding as the coefficient of the sliding friction times the magnitude of the normal force acting on the body. Then the magnitude of the acceleration A is equal to the coefficient of the sliding friction μ, times the magnitude of the normal force n, divided by the mass m. Since the normal force n is equal to the weight of the body, we can write the magnitude of the acceleration as the ratio of μ times the mass m times the magnitude of the gravitational acceleration g, divided by the mass m. Then we obtain the coefficient of the sliding friction μ times the magnitude of the gravitational acceleration g. Therefore, the acceleration A and the velocity v of the sliding body point in the opposite directions, and the magnitude of the acceleration is given by the coefficient of the sliding friction μ times the magnitude of the gravitational acceleration g. As we expected, the body has a constant acceleration, or rather deceleration since its acceleration is negative, and the distance s covered by the decelerating body is equal to the magnitude of its initial velocity times the time t, minus 1/2 times the magnitude of the acceleration A, times the square of the time t. In the case of uniformly accelerated motion, the magnitude of the instantaneous velocity v of the body is given by the magnitude of its initial velocity v0, minus the magnitude of its acceleration A times the time t. When the instantaneous velocity of the body decreases to 0, the body stops. Then its stopping time can be calculated from the equation stating that 0 is equal to the magnitude of its initial velocity v0, minus the magnitude of its acceleration A times the stopping time. As a result, the stopping time of the decelerating body is given by the ratio of the magnitude of the initial velocity v0 to the magnitude of the acceleration A, that is the ratio of the magnitude of the initial velocity v0 to the product of the coefficient of the sliding friction μ and the magnitude of the gravitational acceleration g. By substituting this result into the distance formula, we can write the stopping distance as the square of v0 divided by A, minus 1/2 times A, times the square of v0 divided by A. This is equal to the square of v0 divided by 2 times A, that is the stopping distance is given by the square of the initial velocity v0 divided by 2 times the coefficient of the sliding friction μ, times the magnitude of the gravitational acceleration g. We can also see that the stopping distance of the body is equal to 1/2 times the magnitude of its initial velocity v0, times the stopping time. As an illustration of this phenomenon, let us consider a simple example with a car of 1.5 metric tons, that is 1,500 kilograms traveling with a velocity of 36 km per hour, that is 10 meters per second. If the driver of the car steps on the brake pedals, then the vehicle will slide before it stops. Let the coefficient of the sliding friction μ between the tires and the dry asphalt be about 0.5. By substituting these values into the expression of the stopping time, we obtain about 2 seconds. For the given initial velocity of the car and its stopping time obtained here, the stopping distance of the vehicle will be about 10 meters. We can also study the frictional force produced by a body moving on a ramp under the influence of gravity. In the next experiment, a block with the mass m is sliding down a ramp with the inclination angle alpha. We have already seen that the weight g of the body can be decomposed to its tangential and normal components with respect to the inclination plane of the ramp. Here the magnitude of the normal component of the weight is equal to the mass m times the magnitude of the gravitational acceleration g, times cosine alpha. Similarly, the magnitude of the tangential component of the weight is given by m times g times sine alpha. The net force exerted on the body sliding down the ramp is the vector sum of the tangential component of the weight g and the frictional force, and these forces point in the opposite directions. The normal component of the weight is compensated by the force minus Gn exerted on the block by the ramp. Coulomb's law of friction states that the magnitude of the frictional force exerted on the block is equal to the coefficient of the sliding friction mu, times the magnitude of the normal force acting on the body. In this setup, the normal force is equal to the normal component of the weight g of the body, and we have the coefficient of the sliding friction mu, times the mass m times the magnitude of the gravitational acceleration g, times cosine alpha. Since the block slides down, the magnitude of the frictional force preventing the motion is less than the tangential component of the weight g. We can express the magnitude of the acceleration a of the sliding block from the fundamental law of dynamics as the difference between the magnitudes of the tangential component of the weight g and the frictional force acting on the body, divided by the mass m. By substituting the explicit form of the forces acting on the body, we obtain the quantity of the mass m times the magnitude of the gravitational acceleration g times sine alpha, minus mu times m times g times cosine alpha, divided by m. As a result, the magnitude of the acceleration of a body sliding down a ramp with the inclination angle alpha is given by the magnitude of the gravitational acceleration g, times the quantity of sine alpha minus the coefficient of the sliding friction mu times cosine alpha. A special case of the frictional motion on the ramp is when the acceleration of the body vanishes and the body slides down at a constant velocity. Then the expression in the parentheses of the acceleration vanishes, that is sine alpha 0 minus mu times cosine alpha 0 is equal to 0. In this expression, alpha 0 denotes the inclination angle, where the body has a uniform linear motion on the ramp. As a result, we can express mu as the tangent of the inclination angle alpha 0. Then we can measure the coefficient of the sliding friction for the given pair of materials by finding the inclination angle of the ramp, where the body performs a uniform linear motion under the influence of gravity. If the inclination angle alpha of the ramp can be adjusted, as seen in the figure, we can find an angle where the block slides at a constant velocity on a surface of a given material attached to the inclined plane of the ramp. By varying the material of the block and the surface, we can measure the corresponding inclination angles of the ramp for different pairs of materials in the case of uniform linear motion. For example, if the surfaces sliding against each other are made of steel, then the measured inclination angle alpha is equal to 6 degrees. The tangent of 6 degrees is equal to 0.11, which is the coefficient of the sliding friction between steel surfaces as already shown in a table. The second type of friction presented here is sticking or static friction, which can also be demonstrated with the experiment setup applied for sliding friction. Let's suppose that the block is at rest on the horizontal surface of the table, which is connected to the weight with a string over the pulley attached to the table. The block starts to slide on the surface only if the force F' exerted on the body in the direction parallel with the surface reaches a given threshold. If we gradually increase the force F' by increasing the mass m of the weight, we can find the threshold measured by the spring scale, where the body starts to slide over the table. In this experiment it can be demonstrated that the threshold for the force F' is greater than the force needed to keep the body in motion. If the force F' acting on the body is less than this threshold, then the body stays at rest. By applying the fundamental equation of dynamics, we can conclude that besides the force exerted on the body by the string, there must be another constrained force acting on the body with the same magnitude but opposite in direction. This type of force is called sticking frictional force acting between the contact surfaces of the block and the table. The sticking frictional force resists the force F' applied to the block, and the body remains at rest until this static frictional force is overcome by the dragging force F'. Static friction can also be described by Coulomb's law of friction stating the following. The sticking frictional force is independent from the area of the contact surfaces and directly proportional to the normal force and applied on the body, where the proportionality constant mu0 is called the coefficient of static friction. This coefficient depends on the material properties of the contact surfaces, and always greater than the coefficient of sliding friction for the same pair of materials. The table displays the coefficient of static friction for the same pairs of materials for which the coefficient of sliding friction was already shown. We can see that the coefficient mu0 is equal to 0.6 between bodies made of wood. This value is 0.15 between steel surfaces, and 0.027 between ice and steel. We can also study sticking friction between different materials on a ramp. If we mount a surface made of a given material to the inclined plane of a ramp and place a block with the mass m on the surface, then the weight g of the block can be decomposed to its normal and tangential components with respect to the inclination plane with the angle alpha. Due to the sticking frictional force, Reaction is produced not only against the normal component Gn of the weight but also against its tangential component Gt, provided the tangential component of the weight is less than the sticking frictional force exerted on the body. That is, the magnitude of the tangential component of the weight given by the mass m times the magnitude of the gravitational acceleration g, times sine alpha is less than the magnitude of the sticking frictional force given by the coefficient of static friction μ0, times the magnitude of the normal component of the weight of the block. Then the right-hand side of the inequality can be written as μ0 times m times g times cosine alpha. If we increase the inclination angle of the ramp gradually from 0, the body starts to slide on the ramp at given angle alpha 0. Then the condition states that the tangent of this angle is equal to the coefficient of static friction μ0. Therefore, by finding the inclination angle alpha 0 for which the blocks start to slide down the ramp, we can determine this coefficient for arbitrary pairs of materials.